Okay, we're going to talk about the kinematic equations for constant acceleration. And our goal today is to develop a set of equations that can be used to solve kinematic problems when the acceleration, or for over time intervals where the acceleration isn't changing, where it's a constant acceleration. Okay, now before we get to that though, there is a concept I want to go over that we're actually going to go over in more detail next time when we talk about integration. But it's still a pretty important idea for developing these equations, so I'm going to do that now. So let's suppose we have a little example problem here. Suppose I tell you that the velocity of an object is 2 meters per second, and that the amount of time that we're going here is 5 seconds. So this is, actually I'll put down, this is what's given. And we want to find what is the displacement. So if I say, okay, my velocity is 2 meters per second, and I'm going to walk at a pace of 2 meters per second for 5 seconds, what's my change in position going to be for that time interval? 10 meters, right? I mean, you don't need to do any work to show that. I will anyway. You could say, well, since the acceleration is 0 here, we know that the velocity is just equal to delta x over delta t, right? And since this is a constant velocity problem, so that constant velocity is the average velocity, and this is my definition for average velocity. And so I could say, okay, well, delta x is equal to the product of my velocity times my delta t. Okay? It's a product, velocity times time. Now, I'm going to change this a little bit because since my delta t, what is delta t? Delta t is also known as t final minus t initial, right? Does that make sense? T final. Well, what is t initial here in this problem? 0. We're just going to say, okay, this is 0. So really, t final is just t. So I'm going to change this to v times t. Now this, when you see it expressed like this, you're just assuming that your initial time is equal to 0. And so you're just going to do this. And so you would plug in your numbers now. Okay, my velocity, my constant velocity is 2 meters per second times the time of 5 seconds. 2 times 5 is 10. The seconds cancels the seconds, and you're left with meters. And so, of course, we always have to box our answer, right? Now, this is, of course, unnecessary if you just are thinking about it. Because look, okay, I'm going 2 meters per second for 5 seconds. So I'm going to walk 10 meters. It's easy. So why go through all this? Well, because obviously there's going to be problems where it's a little bit harder. You can't just do it in your head. So you have to write it out. But I'm going to show you another ridiculous way of doing it. You would never solve the problem this way, but it does lead to a really, really important idea. I love graphs. So I'm going to graph the velocity as a function of time. So 1, 2, 3, 4, 5. So this is time in seconds. Thank you. So 1, 2, 3, 4, 5 seconds. And 1, 2. This will be velocity in meters per second. So this is 1 and 2. And of course, in this problem, the velocity is a constant, isn't it? So I'm going to draw it as a horizontal line. Now really, you can think of this as having a 0 slope, 0 acceleration, okay, and it's staying 0. So really, this kind of follows where I'm going. Remember, I said I'm going to talk about constant acceleration in this lecture. Yes, well, here the acceleration is constant. It's 0 the whole time. And so now watch what I'm going to do here. This is super profound stuff. And if you've had calculus already, you'll see what I'm doing here. If you haven't had calculus yet, or if you're in calculus for the first time right now, wow, this is going to really help you when you get to integration. What I've done here is I said, okay, 2 meters per second, and then here's 1 meter per second, 2 meters per second, 1, 2, 3, 4, 5 seconds. Look at these little squares. How many of them are there? 10. And what does each square represent? It represents 1 meter of displacement. You see, if let's take this little square like this. 1 second, 1 meter per second. Now the area, and I'm going to put area in quotes here, in little, air quotes, okay? Area means, width times height. Here's the width and here's the height. So you multiply them together, so you have 1 times 1 is 1. But now, see, look, this is not really a width. This is a time I'm representing with a width. So this is an abstraction. So I'm using a width to represent time. And this is not a width either, or a length. This is a meter per second. So this is an abstraction. I'm representing velocity with the length. I'm representing time with the length. So it shouldn't be any surprise that the area is not area. It represents something else. I'm using area to represent something else. And what it is, it's 1 meter of displacement. Okay? So, because obviously if I go 1 times 1 is 1, a meter per second times a second is just a meter, right? The seconds cancel out. This leads me to a really profound idea. The area underneath a velocity versus time graph represents the total displacement. Okay? Does that make sense? All right. Now, if you accept this, this is true even if the velocity wasn't constant the whole time. Okay, now let me show you this. What if instead of in my example here, what if my velocity started off as being 0 and then it increased at a constant rate to 2 meters per second at 5 seconds? So my velocity at first is 0, but then my velocity, and remember this is a graph of velocity as a function of time. What if it looked like this? Okay? Now, how much did I change my position? Well, at first I'm not going very far at all. And then I go a little farther, a lot farther, and a lot farther. Okay? So what I'm going to do is instead of counting boxes, I'm just going to count. See here, when it was 2 meters per second the whole time, I went 10 meters. Well, here, what does a triangle do to a rectangle? Cuts it in half, right? So this is going to be 5 meters. Now this assumes something though, and it assumes something that I started the lecture with, constant acceleration. I'm assuming here that the slope of velocity, of the velocity versus time graph, the slope is constant slope, straight, constant acceleration. Okay, this is going to be a big idea here in a second. So let's get a little more abstract here and derive an expression. Here's my situation. This will represent velocity. This will represent time. I'm just going to do it qualitatively now, okay? Qualitatively. I'm going to have some starting velocity, and this is going to be a straight line. So if it's a straight line, I can use the linear equation. This is a linear equation. So I start, okay, y equals mx plus b, right? But instead of y, this is the velocity axis. The slope, what is the slope of this? This is delta v over delta t. But delta v over delta t, we have a name for that. It's called acceleration. Here, the horizontal axis, instead of x, we're calling it time. And then this is my b is my value for y when x is 0, but what I should say is it's my value for v when t is 0. Okay? So now I'm going to change the order here, and because it's traditional to write it in a certain order, and it does make sense. You'll see why later. V equals v naught plus a times t. Okay? Now, this is my first kinematic equation. I call it number 1. This is my number 1 kinematic equation. And what I'm going to do is I'm going to develop a couple more. Okay, the next one I'm going to develop, let me zoom out so I can get it on here. The second kinematic equation, what I call the second kinematic equation, is I'm going to say, okay, well, what is my delta x here? How much did I change my position if I started from here and go up here? Well, I just said that the area underneath the graph the area underneath a velocity versus time graph represents my displacement. Well, let's say here's my graph, and here's my area. Well, let me ask you this. Let's see. Let's look at this as a little geometry here, as a geometric shape. This and this are parallel, aren't they? And then this side is not parallel to this side. What name do we have for a shape that looks like that? It's trapezoid. And if you recall from geometry, we can calculate the area of a trapezoid. And what is it? Do you remember? Yeah. Now, for those of you listening online, they all said it's the average base times the height, right? Is that what you kind of said? Sure it is. All right, now, here's what I mean by this. Here's delta x. Delta x is the area, my total displacement is the area underneath the velocity versus time graph. Well, this is my final velocity v. This is my initial. So what I'm going to do is I'm going to treat this like a trapezoid, and I'm going to turn it up sideways like this. So I'm going to treat this like a base and this like a base. So it's the average of these two bases times the height. That's what you learned in geometry, correct? And this is why I like using the document camera, because when I used to do this on a whiteboard, I couldn't turn it over like this. All right, so what I can do is say, all right, delta x then is going to be the area underneath this trapezoidal thing, which is the average base. Well, what is it? Well, it's v plus v naught divided by 2, isn't it? So this is going to be v plus v naught divided by 2. And then what do? I multiply by what I called the height when I tipped it sideways. Well, what is the height here? It's time. And this is my second kinematic equation. That's what I call number 2. Okay? So now both of these equations assume, well, look at equation 1. It assumes that this is a straight line. And if this is a straight line, acceleration is constant. This, number 2, assumes that this is a trapezoid. But if this is a trapezoid, this has to be a straight line. So it assumes, just like equation 1 does, that this is a constant acceleration. Now what I'm going to do is I'm going to play a couple of algebra games to develop 2 other equations. There's 4 total kinematic equations that we use in here. Okay, so let me zoom out a little bit more. Oh, I'm going to have to lift this up so you can see them. What I'm going to do now is this. I'm going to substitute equation 1 into equation 2. That is, what I want to do is develop an equation that doesn't have the final velocity in it. Okay? So it's just a substitution. So I'm going to start with equation number 2, delta x equals, but instead of v, I'm going to say, hey, v, the final velocity, is equal to v naught plus at. So in place of v, I'm going to put v naught plus at. Then I'm going to plus v naught over 2 times time. Okay? So do you see what I did? I just substituted equation 1 into equation 2. And by doing so, I now have an expression that does not have final velocity in it. That's critical. Now I'm just going to clean it up. Delta x equals, well, let's take a look at the top. This is 2 v naughts plus a t over 2 times t. Now, what I'm going to do is I'll go ahead and distribute time in here. So you get delta x is equal to 2 v naught times t plus a t squared. And this, of course, is all divided by 2. And now I'm going to divide both those by 2 and get my final expression. V naught times t plus 1/2 a t squared. This is my third kinematic equation. This is number 3 that I use to solve problems. But again, it has to obey the assumptions made for equation 1 and 2. That is that the acceleration is constant. And next time, we're going to find another way of deriving this equation. Okay, that's going to be kind of cool. Now, I'm going to do this. I'm going to take equation 1, I'm going to solve it for time. So here's equation 1, and I'm going to solve it for time. And because I'm running out of time in class, I'm just going to do it in one step. Time is equal to the final velocity minus v naught. Go ahead. V minus v naught divided by the acceleration. Do you all agree with that? Okay, I just took the first equation and solved it for time. Now what I'm going to do is I'm going to substitute this expression for time into the second equation. So let's do that. I've got delta x is equal to v plus v naught over 2 times this expression for time. Now what this does is that this gives me an equation that doesn't have time in it. That's the goal here. Over a. Now I'm going to clean this up a little bit, and this takes a little more algebra to clean up. Delta x equals, well, let's use FOIL here. V times v is v squared. And then we have v minus v naught plus v naught v minus v naught squared over 2a. Okay? Now, what do we notice in here? This minus v naught plus v naught v, these go away, right? Because it doesn't matter the order of those products. And so now I'm left with delta x equals v squared minus v naught squared over 2a. Now, this is a perfectly good way to leave it, but for some reason in all the textbooks, they rearrange this to, we're going to solve this for v squared. So what I'm going to do is multiply both sides by 2a. When I get that, I get 2a delta x equals v squared minus v naught squared. Now I'm going to add v naught squared to both sides. And what I end up with is my final equation, v squared equals v naught squared plus 2a delta x. And this is my final kinematic equation that I'm going to create today. This is number 4. Now I'm going to show you something really cool. And that is, we can, and I think you'll see why we use these 4 kinematic equations to solve problems. Okay, and I'm going to write them all down here. Here's number 1. And by the way, this is a great thing to put on your equation list that I'm going to allow you to use during quizzes and tests. Okay, so v equals v naught plus at. That's equation 1. Equation 2 was delta x equals v plus v naught over 2 times time. Then the third one was delta x equals v naught t plus 1/2 a t squared. And then the fourth one was v squared equals v naught squared plus 2a delta x. So I'm going to make a little chart here. Now, let me ask you this. What variable is in all of the equations except the first one? What's in this one, and this one, but not in this one? Yeah, delta x, the displacement. No! Yes, yes, yes. Now, what's in all of the equations except this one? What's missing? Well, let's see. This is some time, v naught, v. Oh, acceleration. Yes, no. Yes, yes. What's missing from the third equation? V. Yes, yes. No, the final velocity is not in that equation. What's missing from this one? Time. So yes, 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 no. What's in all of them? V naught. Yes, 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 yes. You always have to know V naught if you're going to use these 4 equations. Now, here's, I'm running out of time, so here's how you use these. When you read a kinematics problem that involves constant acceleration, start off with like given, and then you read the problem. And everything they give you is can be expressed in terms of these variables up here. That's going to be on the homework tonight. So write down what's given in terms of these variables. Then write down what you're trying to find in terms of these variables. Then you do what I call shopping for an equation. You can choose which of these equations, think of it as like tools in a toolbox. Which of these equations can we use to solve the problem? Unfortunately, I don't have time to do an example problem. Also, I want you to read section 2.6. We will go over it next time, but it turns out that gravity near the Earth's surface, gravity has an acceleration of negative 9.8 meters per second every second, or negative 9.8 meters per second squared. And so you just use these equations when it's a gravity problem, when you're throwing a rock off a cliff or something like that. You just use these equations to solve the problem, but you know what the acceleration is. It's negative 9.8 meters per second squared. That's it!